Welcome back. We're going to talk about the heat equation problem. So question 3. This is a little bit different in the sense that it is more of an interpretive question. So what we're looking for is an understanding of what these various terms mean. So in particular, we're talking about the heat equation. So we're talking about the temperature on the vertical axis here with respect to position. So this is a one-dimensional model of a metal bar. Let's get that working correctly. So what's going on here? So again, what do we want? What do we have? And what connects them? So here we're looking for what do we want? We're looking to describe what happens to U1 just after that. And in particular, we want to explain our answer using the heat equation for the full marks. So we've got the heat equation up here. So this is definitely a have kind of thing. And so we want a description. So this means we're going to have to write some stuff out. It's an essay question. And, that gets messy in math class. We'll use purple to answer that just because it's a little bit different. Okay, so what are the things that provide the connection? So we're interested in the position x is equal to 1. So we're interested in focusing on that area right there. And in particular, we are interested in understanding what happens just after t is equal to 0. So for a small value of time, t greater than 0. So this is saying that instead of the partial derivative of u with respect to t, we're going to talk about how u changes with a small step of t. So we're just interested in this as a slope type of entity. And we know from this equation that this is going to be approximately equal to, and let's draw that a little bit better. So that's going to be this diffusion coefficient times the second derivative of u with respect to x. And in particular, we're interested at x is equal to 1. So what does this mean? What does this mean? So the first derivative, if we were looking at partial of u, partial of x, this is equal to a slope. So in particular, the slope here would be 0 because it's a maximum. Likewise, the slope here would be 0 because it's a minimum. Oh, and you can't see that. So partial of u, partial of x equal to 0 because it's a max. And for contrast, partial of u, partial of x is equal to 0 because it's a minimum. That's good old calculus 1. Now, instead, we're interested in not the slope, but the second derivative quantity. I don't like the color. Let's go for that. So we'll do the second derivative, which is how the slope is changing. So this is curvature. So in this case, we were approximating as a line. Here we're approximating as a parabola. And so in particular, if we think about this, this has got a second derivative, which is less than 0, as opposed to, say, here, which has a second derivative, which is greater than 0. So if you think about modeling this as a parabola or this as a parabola, this is going to have a negative coefficient on that x squared term, and this is going to have a positive coefficient on the x squared term. So what do we want to say? So what's going to happen here? So at x is equal to -1, partial of u partial of x squared is less than 0. We don't know how much the value is here. All we know is it's less than 0 because this is a maxima, and that means that the slope's 0 and the second derivative is less than 1. So this is because it's a max. And so because that's less than 0, that means that d times partial of u partial of x squared is also less than 0 because, get a u in there, d is greater than 0. So we've got a positive times a negative gives us a negative. So therefore, delta u delta t, or partial of u partial of t, is also less than 0. So this means that the temperature is dropping for times shortly after t is equal to 0. So temperature is dropping, or it will decrease. So I mean, your keywords here are being able to describe that, that this is the temperature and which direction it's changing. We don't know what the magnitude is, but we do know that it's dropping. All right. So hopefully you did all right on that problem.